So we talk a lot about training set and test set. As I said, the system by default reserve 20% of the data as a test set, but you might want to reserve more. I don't recommend reserve less, but you can reserve more. For me personally, I always like to divide the data into two-thirds train set and 1/3 is a test set. Okay. So what are these train and test set really used for? First of all, the training set, the primary use for the training set is parameter determination for the random forest, right? So, for example, you decide what predictors to use, what threshold to use for each predictor, and so forth. It decides, it uses the training data to build the random forest itself with all the different thresholds and predictor sequence that it needs. And secondary usage of the training set is for feature selection. So after it built this random forest, it will then apply cross-validation on the training set to see what features are actually important. Okay, based on the random forests that are already built, it will select the important features based on the procedure called cross-validation. We'll have to discuss that later. And And based on the selection process, after it selected the top ranked features, it will remove the features from the data set. Okay, so let's say you originally throw in 100 features, 10-day moving average, 20-day moving average, 15-day moving average, whatever, into your feature set. We might decide that only 10-day moving average is important, 15 and 20-day are useless. We will throw them away for you, so as to reduce the noise in your data, and then we will retrain the random forest using the selected feature. So that's the feature selection process, and that's done using by applying cross-validation to the training data. The other process that we apply to the training data is, as I mentioned before, is hyperparameter optimization. What are the hyperparameters? We mentioned something like how many layers of the tree we allow. What's the maximum number of traversal, from the root node of all the data to the grandchildren node with the least amount of data. How many layers do we allow it to iterate? And what is the minimum sample size of the grandchildren, right? And also, like all things like how many trees are in the random forest and how many predictors we allow it to pick from at each node during the random subspace process. So all these are parameters, hyperparameters, and we will optimize them using cross-validation on the train set. Nothing in the test set, by the way, is being used. So the machine learning process doesn't know, basically ignore the test set. Otherwise, it will introduce bias, right? It will introduce look-ahead bias, so it doesn't look at the test set at all. Okay, so, but what about the test set? Well, the test set is for you to see a fair evaluation of how the tree is doing, because the model when we were building the model, it doesn't know at all the test data. So the test data is truly out of sample, and you can evaluate your performance on the test set. But there's a problem. There's a caveat. Nobody, or I would say very few people, is successful with the first machine learning model, with the first set of features. Most likely, you are going to get a subpar performing model. But nobody should give up, because at that point, it is time to change your feature. Maybe there's some extra feature you might want to add, or maybe the features that you pick are not properly engineered, right? So, for example, what is a good example of a improperly engineered feature? Yes, one which certainly is let's say you are trying to predict stocks, a universe of S&P 500 stocks return, and then maybe one feature that you included are the volatility of the stock, and the feature that, but the problem is the volatility of different stocks are very different. The volatility of a penny stock might be 10% a day, not a year, whereas the volatility of ExxonMobil might be 10% a year, right? So they have a big difference in volatility. If you just put all the stocks together in the same data set and just say, okay, volatility is one feature, your feature will not be very informative. It won't be very predictive because they represent completely different animals. You are mixing apples and oranges. So feature engineering would require that you will normalize your volatility in some manner so that they are comparable between different stocks. So that might be an example of a misengineered feature. So when you see a bad result, you will go back to your feature and think long and hard how to make them better. But the problem is every time you re-engineer your features and you rebuild a new machine learning model, random forest as a result, you will have to look at the result on the test set again to decide if this model is better. But after multiple testing, your test set is not really out of sample anymore because you have used that test set performance to judge whether you should include certain features, right? How you engineer existing features. So after a while, as long as you have looked at the test set performance more than once, you are gradually turning your test set into part of the training set. You are using your test set to optimize your features.